Hey everyone, in this video I wanted to take some time to talk about computing volume, area, and curve length using integration because I've gotten a lot of questions recently about, okay, how do you find, say, the volume or the area in particular of a non-rectangular region to be able to use it for, say, like average value or something like that. And then we're also kind of moving into this area where we're working more and more with line integrals and integrating over curves and stuff like that. So that kind of seemed like a really good opportunity to tie this into finding curve length as well. So let's go ahead and start by looking at an overview of just the general idea behind finding these values, and then we'll work an example for each one. So overall, the idea behind actually all three of them is really quite similar. For the case of volume, we're looking at a triple integral, and to get volume, what you do is you take a triple integral over that three-dimensional region that you are looking at. We can call it omega or something like that. And the function that you're going to integrate in that case is just going to be a 1. Okay, you're not plugging really anything in. It's just a 1. And then you, of course, have your dv there, where the v is volume. And really all this is saying is that we're chopping up our space into whatever this region is that we're working with into a bunch of tiny little pieces represented by dv. And then we're just going to add them all together and multiply them by each other in order to be able to account for all the different dimensions that we've got. And the reason that we have the 1 here instead of a regular function is because we don't really want to take into account any variation in sort of like density, if you will, or any changes over the makeup of the region. We just really want to focus on the overall shape, chopping it up into tiny little pieces and combining them all together. And we can apply the same idea for the area as well. And we're going to do a double integral because we need a double integral to get area. And then over our region omega that we're curious about. And then of a 1 again as well, and then dA this time instead of dV. Again, for the exact same reason, we're taking our region omega, chopping it up into tiny little pieces as represented with the dA there, and then kind of adding them all together and then multiplying our two different dimensions together using that double integral. And then finally, as you might suspect for curve length then, well, instead of looking at like a region, if you will, we're looking at, well, a single integral over a curve, say C, and the length of this curve C is given by, well, a 1 and then ds, where S is our curve chopped up into tiny little pieces, and then we just add them all together. So, main idea, we set up the bounds for your region or curve, and integrate with the function inside being just the number 1. Okay. So let's look at some examples for this. Our first example is going to be for volume. So we are going to compute the volume of the shape bounded by the plane, let's say 3x plus 2y plus z equal to 6, and we want it to be in the first octant. So just so you can know what region I'm looking at, that's going to be, if I draw my x, y, z axes here, x, y, z like so. This is going to be my first octant, is this part right here. And then the region we're specifically interested in will be here. So if we wanted z to be equal to 6, that's going to be my upper corner up here. And then y would have to be equal to 3. So we're isolating the y and then solving for it. So you just get y equal to 3. And then the same idea with the x, you get x has to be equal to 2. So then the region that we're interested in is this tetrahedron shape right here in the first octant, because this triangle here represents kind of like our plane slicing through the space, and then we just have the area that's underneath that, like so. Okay, so that's what we're interested in. And then I'm not going to go into too terribly much detail on like how to get the bounds, but just the main idea here is that we want to set up, we have this triple integral over our region of 1 dv. The dv is going to become, it really doesn't matter what order we integrate this in. So I'm just going to say dz, dy, dx, because I mean, that one's pretty common. So I just got to figure out my bounds of integration here and then actually integrate it. So here's my integral. I have a 1 and then dz, dy, dx. And again, not going into too terribly much detail, but just kind of going over the main idea here. We want all of these to be greater than 0. And then we're integrating z first. And since I want it to be bound by this plane, I know that I need z to be, we can think about this as actually being a less than or equal to. And solving for z to get its bounds, I need z to be less than or equal to 6 minus 2y minus 3x, okay? And that accounts for just like all of these values here along the slope here, instead of just saying, okay, I want z less than or equal to 6, but I also want to account for everything out here as well. So this is going to be 6 minus 2y minus 3x. And then I need y. Now that we've kind of eliminated z, all I got to do is rearrange this guy for y. And what I get from that is 3 minus 3 over 2x. Like so. And then finally, having eliminated y, I just have to solve for x here. Or now that we're down to just a single variable, I can finally look at the axis that x is on and just say that, okay, x can only go out to 2. And like I said, all of these have to be greater than or equal to 0. Okay, so now I've got my integral, and you can go through, compute this the same way that we did previously. I don't want to go through too much of the mechanics of this because I just kind of want this to be a quick example, but I will tell you that the final answer that you get here will be 6 units cubed. So 6 units is really just the volume of this tetrahedron shape right here, which we got by saying, okay, I've got these bounds for the region, and I've got these kind of like this region that's been chopped up into the little pieces, the dz, dy, and dx. And instead of integrating over a function this time, I'm just going to put in a 1 and say, all right, I just want the volume. I don't really care about how anything in like the density of my shape is changing or anything like that. So what we've done here is we're saying, okay, chop the region in the z direction, and then get that total, multiply it by it chopped up in the y direction, get that total, and then finally multiply it by it chopped up in the x direction. That's not exactly what's happening, but it's kind of like a heuristic for it. So, all right, so that's an example for volume. Let's look at an example for area. So in this one, we are going to find the area between the two curves f of x equal to 3x squared minus 2 and g of x equal to x squared. Okay. So you've probably seen a problem that looks exactly like this before in like a Calc 1 class or something like that, and you absolutely could approach this using Calc 1 techniques. But I kind of want to show you how this ties into, well, what we've worked with the iterated integrals. So looking at this region, we're going to get something that looks kind of like this. So that x squared, I'll plot that one first. Is going to look something kind of like this. And then my 3x squared minus 2, I'm going to go down 2 units. So 1, 2 for the vertex. And then what it actually does is it comes up and slopes up like this and intersects with the x squared there at 1, 1 and negative 1, 1, like so. Just like that. And so the region that we're looking at is then going to be this area right in here. So it's going to be kind of like in the, this is the part that we're really curious about. Okay, so using these new Calc 3 methods that we have to be able to find the area, we can look at our double integral over our region omega, put a 1 in, and integrate with respect to the dA there. And this will also give us the area in here, just the area, because we only have a 1 plugged in. We're not integrating with an extra function or anything like that that tries to take some sort of density or anything into account. So all we got to do is determine the bounds for this guy, and then integrate. And so as far as determining the bounds for this, I think that it would be best if we integrated using, if we did y first, because this means that we want to use vertical slices. So we're going to slice kind of this way, like so. Just because it makes it a lot easier. Everything's always following one rule if we slice that direction. So following that particular setup using vertical slices, we're noticing that y is always bound between, well, this guy down here is my 3x squared minus 2. So this is always underneath y. So I have 3x squared minus 2 is always less than or equal to y. And the x squared is always above y. So y has to be less than or equal to x squared. And then looking at side to side now, x is allowed to range from -1 to 1. And you can get that by finding the point of intersection between these two right here. So -1 less than or equal to x less than or equal to 1. These are the points of intersection. Okay, so if I want to set up my double integral here, then what I'm going to get is the integral. We'll set these up first, and then we'll have the 1 dy dx. So dy on the inside, I need my y bounds on the inside. So 3x squared minus 2 up to x squared, and then my bounds for x are going to be on the outside. And this one I will actually work in a little bit of detail because I want to emphasize something. So if I go through here, we get -1 to 1, and I'm going to have integrating with respect to y first. I get y right here, evaluated from 3x squared minus 2 up to x squared dx, which gives me -1 to 1 of x squared minus 3x squared minus 2 dx. All right, now that right here should look familiar. In particular, that is exactly the setup that you would have gotten had you used Calc 1 methods. Okay, so and my point with that is that this particular method right here of setting up the double integral and doing dA and getting your bounds like this, as you go through it, you actually wind up with the result that is exactly the same. You wind up catching those same steps that you did in Calc 1. So it's really just that this is a more general setup. It's a generalized setup of what we talked about, what we would have talked about in Calc 1, with taking the upper function minus the lower function and then integrating over that instead. So the main point here is that your two methods are equivalent. So when you're looking at area, you can actually really use either one depending on the setup and stuff. So just kind of a fun little fact there. Now, at this point, again, you just integrate this part really straightforward, and what you get is 8/3 units squared for your area right there. And yeah, that's pretty much all there is to finding area. Again, double integral with your bounds according to what your region is. You put a 1 in instead of an actual function, and then you just integrate as normal. And it happens to wind up being equivalent to what you did in Calc 1. So that's pretty cool. All right, let's do curve length now. Last example. So for this one, we will find the length of the curve, let's say y equal to x to the 3/2 when x is between 0 and 4. So we had said earlier that if we integrate over the curve with a 1 plugged in, and then we have ds, then we're going to get our curve length. And this particular curve looks something kind of like, I guess we don't really look at this particular curve too much. It looks kind of like an x squared, x cubed type function. I guess the way I've drawn it, it looks like x squared, but it's kind of like a really flat x squared. But anyway, in order to be able to integrate this, remember that integrating over a curve if we have fxy, for example, ds, then this is equal to the integral of, or if we're integrating a function over a curve, then we have to reparameterize it, plug in that parameterization, multiply it by the derivative of that parameterization, and then the norm of that, and we'll use this for our integral instead. So in this case right here, our area, or our arc length of this curve C between 0 and 4 is really just going to wind up being our integral from a to b, whatever bounds we wind up putting on that. And then this function right here that would normally be, this function right here is really just a 1. So we just wind up with a 1 over here. So it's a 1 times length of r prime t dt. Okay, so and actually this right here, if I ignore the fact that the 1's there, which you really just kind of can, that should look really familiar to you. In particular, we talked about this particular integral when we introduced the notion of arc length back when we first started parameterizing lines. So this is just exactly that same formula all over again. Nothing new. Nothing new at all. We're just actually applying it now. And so let's go ahead. We just got to find r prime, and then the length of that. So parameterize y equal to x to the 3 over 2. In this particular case, when I'm given something like this, we just want to take x equal to t and then plug that in. So y is now going to become t to the 3 over 2. And my bounds on x or on t are really just the same as the bounds on x. So t is between 0 and 4. So r of t is equal to t to the 3 over 2, which we really don't need r of t itself. We're more interested in r prime of t, 1, and then 3 over 2 t to the 1/2, which means that the length of r prime of t is equal to root 1 plus, you're going to have 3 over 2 t to the 1/2 squared, which is just equal to root 1 plus 9 over 4 t squared. Oops, not t squared, t. Okay, so then setting up this integral just becomes integral from 0 to 4 of root 1 plus 9 over 4 t dt. Okay, and actually this is really quite, oh no, this is fine. Yeah, so at this point, it's really actually quite straightforward to integrate. You can just use some u sub, and it's really quite friendly. We let u be equal to 9 over 4t, which means that you're going to get du equals 9 over 4 dt. Well, I don't have a 9 over 4 out here, so I got to rearrange. 4 over 9 du equals dt. So my integral of root 1 plus 9 over 4 t dt is now going to become 4 over 9 integral u to the, oh, that should be a 1 plus 1, and that goes away. U to the 1/2 du, which is just equal to 4 over 9 times 2/3, and then u to the 3 over 2. So, okay. So that means that my integral from 0 to 4 of root 1 plus 9/4 t dt has to be equal to, what you're ultimately going to get is 8 over 27, 1 plus 9 over 4 t rate, or evaluated from 0 to 4. And yeah, that you can just really just throw into your calculator. So I'll leave that part to you. But anyway, the big idea behind this was to set up the bounds, integrate over 1. in each and every single one of these cases. So if we go back to our first page here, this is really the big thing that we want to be looking at here whenever you're looking for volume, area, or curve length. So, and that said, if you're ever asked to like interpret what something like this means, like suppose that you're given, you know, one of these three here, and you say, okay, well, what does the triple integral over just one mean? Well, that gives me volume. Or for area, what does the double integral over just one mean? That gives me area, or oh my goodness. Okay, this gives me area. And then curve length, if we integrate over a curve with a 1 in here, then we just get the curve length instead of anything that takes into account some sort of density or anything like that. So really quite nifty. Hopefully this has answered some questions for you and cleared some things up. So yeah, that's pretty much it for this one. I'll see you guys next time.